Okay, in today's applications lesson, applications of exponential functions, we're going to be first of all visiting a formula you saw back in integrated algebra. And it was the formula for calculating the final amount of something that you had. You started with a given amount of money or a given value, and then it either went up or went down. It either appreciated or depreciated over a certain period of time. So the formula looked like this that you used. We won't use that formula too much in trig region, so oftentimes these kinds of formulas will be given to you. But let me just go through a quick run through of what we did back there. I like to call this the T because that's the total amount we're left with after it's all said and done. So, and that was a formula that you had to memorize freshman year, if you recall that. The P represented the principal amount or the amount you started with. And then if things were appreciating, the value was going up, you would add. If things were depreciating, the value was going down, you would subtract. The important thing to remember with this rate, the problem would give you a rate, and the problem would also give you some period of time. But the important thing to remember with the rate and the time is that those chunks of time, the units there, had to match. If your rate was given in terms of months, then the T, the term or the number of months, had to be in months. If your rate was given per year, then you'd have to have year up here. You'd have to make them match. So you'd have to decide which one you wanted to use and force the other one to match if it didn't already. And as long as you did that, it was a simple plug-in. Everything would work out fine. Okay, so let's take a look at this problem here. This problem, typical 1-hour problem. Sylvia deposits $500 into an account, assuming she makes no additional deposits or withdrawals. She goes 10 years and she's earning money at the rate of 6.5%. Now this problem doesn't say it's 6.5% quarterly, but it says it's going to be compounded quarterly. So we're going to have to use quarters as our term here. I like to start these problems out by specifically writing out what we're working with, and hopefully that'll catch any errors you have as far as matching things. We need the total amount after 10 years. She starts with her principal amount, $500. The rate that we're using, now this is compounded quarterly at 6.5%. It really doesn't tell me what that rate, that percent is. I could assume it's 0.065 per quarter. That's pretty darn high. That's a great, if you can get that account, you want it because that's a great rate. I think that the intent here was to say that's an annual rate, but you know what? I'm going to go with a quarterly rate and we'll see how many millions of dollars she's going to end up with. So we want to express that R as a decimal. That's why I converted to 0.065. I'm going to say that's per quarter. And the term is how many quarters we're going to be looking at. We have to use quarters as our term. And so how many quarters are in 10 years? Well, that's going to be 40 quarters. And so we'll start doing our plug-in here. The total amount she's going to end up with is $500 times 1 plus 0.065 raised to the 40th power. I think she's going to be a millionaire. I'm going to grab the calculator and take a look at that. It's going to be, we'll go to calculations page. And it was 500 times, and I'm just typing this into my calculator the way I see it, 1 plus 0.065, close the parentheses, use your caret key, and we'll raise all that to the 40th power. Oh, she's not quite the millionaire I thought she was going to be. She's only going to have $6,200 at the end of 10 years. But let me tell you, $6,200 for a $500 investment after 10 years is a darn good amount of money. So that rate probably was supposed to be annual, but it doesn't say. In a problem on a test or Regents exam, it would say. So your total value at the end of all that time is $6,208, or whatever the calculator said. Okay, well, typically you're going to get a, you might get a new equation. Just a word on this problem here, the decay constant of radium is minus 0.0004. We're using the same type of equation here. We want to know what's left after 20 years. T, the amount left after 20 years, would be equal to what I started with. In this case, oh, we don't know what we started with, so we're going to have to come up with a new formula for this. And typically, like I said, the formulas on the test or on the Regents exam will be given to you if you're dealing with these kinds of problems. In a problem such as this, or in a problem where we have continuous compounding of interest, well, we don't stop every now and then to give interest to the account. We just are constantly, on a routine basis, we're giving money to that account. In this case, the radium is going to constantly be decaying. It's not going to, decay for a day and then stop and then come back a week later and decay some more and then stop. So when we're dealing with a problem like that, we have a slightly different form of an equation. If you know what Pert shampoo is, that would help you remember the form of the equation. It's the principal, and then we use a special constant. It's an irrational number called E, and you have a key for that on your calculator. It's PE to the, grab the green here, to the RT. And again, a lot of times these formulas are given to you. So let's look at what the principal amount is here. We're starting with a 50-gram sample. We're going to use that special E key on our calculator to represent that irrational number, and we're going to raise that E to R times T. Well, R is my rate of minus 0.0004, and my units here are 20 years. And that constant is in terms of years, so I have no problem with units not matching. And then we'll pick up our calculator and we'll type that into our calculator. Use your caret key to get the exponent up there, and it'll tell you how much is left after those 20 years. Okay, the last thing I want to take a look at here is what happens when you are given an equation which represents some growth or some decay. In this case, it's growth because I'm looking at 1.05. I added a number to that 1, so I know that this is going to be increasing over time. And it's going to increase exponentially. T is representing time, but T is what you'd put on your x-axis. You can't use T's in your calculator. I've got a graph page ready to go here. And the first thing I'm going to do if I see an equation like this, I'm probably going to be asked to graph it on my paper, so I'll need to put it into the calculator to get some values from my table so I can start plotting it. I'm going to be in my calculator to stop that little noise. So I'm going to go to Control G, put a graphing line in there, 150,000 plus 15 times 1.05. I'm pretty much typing it the way I see it, and remember you can't use T's, you have to use X's, so we'll put a caret in there and put an X up there, and I'm going to hit the enter key and I'm going to see nothing. The reason I'm seeing nothing is because this graph is way off, and so I have to try to figure out where it would be. Well, this 150,000 says that it's going to be a whole lot higher than 6.57. I guess what I'm going to do, it's going to go up from there. So I think I might want to see up to 300,000 on here and see what happens when I do that. You can just double click on that number and type it, and now we're looking for that exponential function. I don't need the negative numbers because time is never going to be negative. So I'm going to change that minus 10 instead to a 0. And I'm going as far out now as I can't even see what that number is, but it's going to be too small for me. So I'm seeing a horizontal line. I'm looking for an exponential equation, so I'm going to change this here. Okay, well I changed it to a 200 and I found my curve. It's right here, but obviously I didn't know it needed to go out that high. Let me go back to 100. And you're going to see me playing around with the settings here, and yep, that's what you have to do with these if you want to find what you're looking for. Let's see, it looks like that's not enough. Okay, I actually had made it much bigger than 200. I think I accidentally typed a 0. Okay, so there's the exponential equation that I'm looking at. And now I could go find my table of values and I could start graphing. I'm seeing the exponential curve in here. So if I did a Control T at this point, you'd be able to find your table and start, finding all your X and Y values and plotting them as you need them. Now, if I asked you what happened at t is equal to 4, you can look at 4 and you can read the number off and you can tell me what's happening. Or you could go to 4 on the x-axis and you can read up to your curve and that would tell me what's happening. But what happens if what I want instead is to know where the answer is equal to 200,000? I want to know like how much time has to pass before I get to 200,000. Well, you're not going to be able to find that in the table. It's unlikely you're going to get an exact 200,000 in the table. And we're going to be scrolling a long time here because this thing grows slowly at first and then it starts jumping. I'm still in the 150,000. I'm going to go up a whole lot faster than that. I'm going to have to wait for my computer. Grab the slider there. Okay, 151, and again, I wanted to go to 200,000. All right, well, by the time my t is 166, I'm getting close to 200,000. By the time it's 167, I'm over 200,000. So you can't use your table to do this. What you're going to do is you're going to put a horizontal line on your graph. I'm going to Control G and go back to my, or Control T, sorry, to go back to my graph, and I put a horizontal line on this graph, and I can put that horizontal line at 200,000, and then you'll see how easy this is. If you do a Control G, y equals 200,000. Now you've got a line, and now all you have to do is find the intersection between that line and that curve, and it'll tell you exactly what t is when you get to 200,000. Well, it'll round it off to a couple of decimal digits, but it's going to be good enough for you. So we'll do the menu, we'll do Analyze Graph, we'll ask for the intersection, the lower bound below the intersection point, and click. Move the upper bound above the intersection point and click. And you can use your grabby hand. You can Control click and grab that label and move it off so you have a better chance of reading it. And now it says that your t value is exactly 166 by the time you get to 200,000. And that's how you're going to find your answers if the value I'm giving you is the value. If I'm giving you the value and asking you how long it took to get there. Again, this is an equation that has time on the x-axis, but you're going to have to play around with those settings in order to find these curves. These are real-world applications, so they're not going to all fit nicely in a 10 by 10 grid. So you'll just get some practice playing around with it and finding the curves there.